Welcome to the Ultimate Exam Strategy Briefing. Think of this explainer like Ocean's 11, but instead of robbing a heavily guarded casino vault, we're assembling a team of cognitive specialists to pull off the absolute perfect heist, cracking the Cambridge computer science exams. And look, whether you're sitting for syllabus codes 0417, 0478, 2210, or 9618, the vault door remains exactly the same. You need a foolproof system to bypass the examiner's traps. Now, let me introduce you to two students who perfectly represent the classic traps you might just fall into if you're not careful. First up, we have Alex. Now, Alex is a walking, talking encyclopedia of tech. When faced with a question, Alex absolutely overloads the page with raw computer science facts. We're talking spilling every single bit of knowledge onto the paper, but offering absolutely zero analytical depth. It's like bringing a sledgehammer to pick a delicate lock. Then, on the other end of the spectrum, we have Sam. Sam is the sprinter. Sam rushes through the paper at lightning speed, completely misses the critical command word requirements, and drops massive, incredibly easy marks. Sam is basically the getaway driver who speeds off before the vault is even open. Today, we're going to look at their flawed answers, break down exactly where they went wrong, and completely rebuild your approach so you never, ever make these mistakes. We're tackling this entire strategy through the lens of binary addition and overflow applications. By the end of this session, you won't just understand the raw math, you're going to understand the underlying matrix of the exam itself. Let's get to work.
All right, let's look at this real-world past paper question. What happens when a digital device runs out of processing space? This right here is exactly the kind of question that triggers instant panic in an exam hall. When faced with this exact prompt, let's see what our friend Alex writes. Alex says, binary is composed of ones and zeros, and computers use an 8-bit or 16-bit register, and when you add 1 and 1, it equals 1, 0. Okay, do you see the problem here? It's factually true. Every single word is correct, but it gets absolutely 0 marks awarded for the actual question asked. It's just a data dump. Sam, on the other hand, in a total rush, just writes, the computer crashes because it's full. Wow. Cue the red pen all over the page. Both of our students completely missed the target. Why? Because they view binary addition and overflow as these isolated, boring math facts, rather than practical, real-world digital phenomena. To secure those top-tier marks, you have to understand that an overflow isn't just a tiny carry bit falling off the end of a register in some textbook. It is a critical, cascading system failure with actual real-world consequences. So we're going to fix Alex and Sam's answers by applying a true cognitive heist strategy.
Okay, let's dive into this strategic map. Here is our absolute blueprint for the perfect answer. Number 1, the real-world context hook. Number 2, defining core concepts. Number 3, the technical answer methodology. This is the core vault, where we'll reveal the Peel framework. Number 4, avoiding classic exam errors. And finally, number 5, the ultimate memory matrix.
Section 1, the real-world context hook. Let's get straight into it because we're taking a strict application-first approach. Here is the secret examiners desperately want you to know. Top marks in Cambridge computer science aren't won by writing short, detached, generic labels. They are won by demonstrating deep application-first understanding. And how do we do that? By using what we call the Peel framework. That stands for point, evidence, explanation, link. Now, when a question asks you about overflow, your point is the crisp definition. Your evidence is the specific binary addition itself. Your explanation is the hardware limit literally being exceeded, and your link, which is honestly the most absolutely crucial part of this whole heist, is connecting that technical failure back to the specific context provided in the question prompt. Let's really put this framework to the test. Imagine the exam asks about a secure banking system. If you pull a Sam and just say, an overflow error causes a crash, congratulations, you get exactly 1 mark. But if you use the link stage of the Peel framework, you say, an overflow error in a secure banking system's arithmetic logic unit could result in an incorrect transaction value being stored, leading to massive financial discrepancies. Boom, full marks, flawless execution. Now think about smartphones and media processing. If an image processor tries to add binary color values together to increase the brightness of a photo and it overflows a strict 8-bit limit, the color doesn't just get brighter, it wraps all the way around to 0 and suddenly turns pitch black. In robotics and industrial control, an overflow in a timing sensor could cause a massive mechanical arm to just swing wildly out of bounds, potentially causing a disaster. In school and retail networks, an overflow in a database index can permanently corrupt student or customer records. You must constantly ask yourself what digital problem is actually being solved or created in the specific, exact context. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Making the terminology meaningful like this is exactly how you unlock the highest grade boundaries.
Section 2. Defining core concepts. Now that we have the context, we need to build our theoretical foundations. We need to know exactly what we're looking at.
Okay, commit this to memory. Here is your gold standard examiner-approved definition. Binary addition in overflow is a process where binary numbers are added, and overflow occurs when the result exceeds the allocated memory limit of the system. Let's do a live 60-second mental rewrite for our two struggling students. Alex needs to totally stop writing about the ancient history of ones and zeros, stop rambling, and just write this exact definition. Sam needs to stop saying vague things like "it crashes" and start explicitly saying the result exceeds the allocated memory limit of the hardware. Do you see why this specific wording instantly adds marks to your score? It actively proves to the examiner that you understand both sides of the coin, the mathematical action taking place, which is adding the binary numbers, and the hardware consequence, which is exceeding the allocated memory limit. This right here is your computer science success blueprint. You're not just reciting math, you are proving a deep understanding of software logic, violently clashing with hard, physical hardware limitations.
Now, what's really interesting about this slide is that it highlights a massive trap, a trap that even top-tier students fall into all the time. They confuse nearby, similar-sounding concepts. Year after year, examiner reports consistently highlight that candidates totally mix up logic processing with arithmetic processing. Let's clear this up right now. Arithmetic processing involves mathematical operations. It's like our binary addition, where a carry bit physically requires more register space to exist, and if it doesn't have it, it leads directly to an overflow error. Logic processing, however, involves Boolean operations. We're talking your AND, OR, and NOT gates. These evaluate true or false states, and they do not inherently generate mathematical overflow in the same physical way. By contrasting these two concepts directly in your exam answers, you sharpen your analytical precision to a razor's edge. If the exam asks you about an arithmetic logic unit, or ALU, you need to know exactly which side of that unit is failing during an overflow event. It's the arithmetic side. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. The technical answer methodology. Let's shift from theory to application. This is the disciplined path required for true examiner-style performance.
All right, team, let's walk through this 4-step technical methodology. This is how we decode the exam. Step 1. Identify the exact task requirement. You have to decode the command word. Is the examiner asking you to state, to describe, to explain, or to evaluate? A state question needs one sentence. An evaluate question needs a full, balanced argument. Don't be like Sam and skip this. Step 2. Classify the relevant data and hardware. Are we talking about a simple 8-bit register, a complex 16-bit color value, or maybe an embedded system in a washing machine? Know your hardware. Step 3. Explain the process in a clear, logical sequence that another learner could actually follow. Walk them through the binary addition step by step, showing exactly where the math breaks. And Step 4. Connect to context. I cannot stress this enough. This is the final step, and anchoring your explanation to the specific scenario provided is where the real top-tier marks are won. If the question is about a cybersecurity incident, your entire answer must stay inside the context of security. Without Step 4, your answer is just floating in the void. It's generic. And let me tell you, generic answers rarely, if ever, gain full marks in Cambridge exams.
Section 4. Avoiding classic exam errors. Let's introduce the wrong turns. Think of this as your personal defense system against losing easy marks.
So, the crucial point is this. Specificity is absolutely everything. Let's run a quick interactive workshop right here. Look at these points. These aren't just guesses. These are the actual trends extracted from years of real Cambridge examiner reports. We're going to do a Find the Flaw challenge. Ready? Imagine a sample paragraph from a student that reads, "An overflow error is bad. It happens in memory. The system uses verification to check it." Okay, you have 60 seconds on the mental clock. What are the fatal flaws here? Let's break it down. First, saying "is bad" is incredibly vague and generic wording. Examiners hate bad. Second, just saying "it happens in memory" completely misses the critical process steps of exactly how the register capacity was exceeded by a carry bit. Third, saying the system uses verification is confusing similar terms. They almost certainly meant validation or simply error checking protocols like parity checks, not data entry verification. And finally, they completely failed to answer within any given context, and they named a method without explaining how it actually works. If you just write down everything you know without direction, like our friend Alex, you will fail to secure the marks. Always write with surgical precision. Now let's wrap up this interactive segment with a high-pressure, 30-second mental speed writing challenge. Ready? In your head right now, try to compose one perfect POL paragraph, explaining how an overflow error affects a digital stopwatch. Go. Okay, here is the perfect answer. Point: define the overflow. Evidence: the binary counter mathematically maxing out its bits. Explanation: hitting the physical hard limit of the device's register. Link: the stopwatch catastrophically resetting to 0 prematurely, completely ruining the Olympic athlete's recorded time. If you can do that under pressure, you are ready for the final systems.
Section 5. The Ultimate Memory Matrix. This is it. The final systems that guarantee your exam readiness through structured repetition and active recall. This brilliantly illustrates our 3-pass revision cycle. It's not about reading a textbook once and hoping for the best. It's a timeline to absolute mastery. Pass 1. Secure your key definitions and contrasts. This is the foundation where you ensure you will never, ever confuse arithmetic processing with logic processing again. Pass 2. Rehearse worked explanations. This means actively practicing the step-by-step binary addition on paper and tracing exactly where that sneaky carry bit falls off the edge of the register. Do it until it's muscle memory. Pass 3. Adapt to changing scenarios. This is the magic step. This is where you move from basic, robotic recognition to true exam adaptability. You take the exact same core concept, Overflow, and practice applying it to a robotic manufacturing arm, and then apply it to a secure banking database, and then to a glitching smartphone display. This layered, flexible style of study is deeply, deeply important because Cambridge computer science questions relentlessly combine theoretical knowledge with applied, situational reasoning.
And that brings us to the final piece of our perfect heist, the 4-prompt memory structure. This right here is your ultimate mental cheat sheet. It is the absolute final checklist you must mentally run through before putting your pen down and submitting any exam answer. If you cannot satisfy this simple structure, your answer is incomplete. Students who implement these computer science strategies see an average improvement of 2 full grade boundaries. But of course, that's only if they practice consistently with our weekly explainer sessions. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at Exams IGCSE, to excel in your Cambridge examinations. Subscribe right now to @Ace the Exams IGCS and click that bell. Don't let another exam pass you by without having the best strategy possible.
So here they are, the final 4 prompts. What is it? How does it work? Where is it used? Why is it better or worse? I want to challenge you, right now, to answer these exact 4 questions aloud during your very next study session. What is binary overflow? Seriously, say it out loud. How does the addition process practically cause it? Where is it actively used, or where does it fail in the real world? Drop a comment below with your target grade for computer science and the absolutely biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Because at the end of the day, I leave you with this one thought. If you can't manage a simple binary overflow, who is really in control, you or the machine? Good luck on your exams and keep pulling off those perfect answers.